So let's continue with this example. Determine the actual compressive strength of an HSS 8 by 4 by 1/8 with an effective length of 15 feet with respect to its principal axis. Use Fy is equal to 46 KSI. To get the or to determine the properties, no, you can, like I think I discussed this one in the AISC. Let me show you. Still detail. Kani siya. I think I posted the link for this one. Yes, there are different sections like WMS, HPC, MCL, and since the problem is HSS, so we try to see under the HSS specification, no? And HSS 8 by kuan 8 by 4 by 1/8, no? I think 8 by 4 by 1/8, yes. Actually, andam ko na ni siya daan para dili ta malangan. Okay, bugat ra ba ang kuan recording. So, yes, HSS 8 by 4 by 1/8. Then you will see the area of the section is 2.7 inch square. The nominal weight is 9.86. The width is 4. Height is 8. The web thickness is like 0.125 for the nominal web thickness. For the design thickness, no, is 0.116. Or this is 0.93 times the nominal thickness. So, ang ginagamit sa computation, no, is the design thickness, which is in here, the HSS 8 by 4 by 1/8 is 0.66 inch. So, ano siya, no? Then, first, we compute for the slenderness of this or the global buckling strength, no? We try to determine the global buckling strength. So first, we have to compute the slenderness ratio, the KL over R, no? It should be maximum. So to get the maximum, this R here, the radius of gyration, should be, as we discussed already, should be the minimum radius of gyration or the R sub Y, no? This is can be seen in the table of values from the AISC manual. And L, since this K, so if it is not a given, wala siya gi-indicate, no? I think this is like the K, you assume that this is 1.0. So siguro perhaps the connection, no, is pin to pin. So this is K equal to 0. Then L, this is in feet, no, to convert to inches times 12. So RY, this is from the table. I don't know if kuan ba ta? The HSS 10. This is the AISC manual, the 14th edition, no? HSS by HSS 8 by 4 by 1/8, no? Your radius of gyration should be the R sub Y. This one. Let me. So for here, the radius of gyration along X, Y, Y, no? Along the axis, along X, Y, Y. Along the axis Y, Y should be, in here should be this, along the axis Y, Y. Radius of gyration 1.71. No, 1.71. So the maximum KL over R is 100 5.3, which is this 200, di ba? We discussed this one in the previous video. The limiting value, no, should not exceed the 200, which is okay. Wala man siya nilapas og 200. And we also compute for the this limiting value 4.71 square root of E over Fy. E for steel is 29,000 KSI and Fy is indicated 46 KSI. The value is 118, which is less than the slenderness, greater than, no, than the slenderness ratio KL over R. This is for the global buckling, no. Then since 105.3 is less than 118, use the INSCP equation 505.3-2 or the AIS equation 3-E3-2 for the Euler's buckling strength is equal to this one, diba? You compute for the Euler's or F sub E, pi squared E over KL over R squared, no? Which is equal to 25.81. And since this KL over R is less than 4.71 square root of E over Fy, we use this critical buckling load, no, equal to 0.658 Fy over Fe. Yes, I think we discussed this one in the previous video. Okay, atong balik ko, no, for that, yes, this one. Equation 505.3-2 or AAS equation E3-2 when KL over R is less than or equal to 4. Now this is given in the code. Use this FCR or the critical buckling load equal to 0.658 Fy over Fe times Fy. So let's go back to the problem. Where are we? Ano naman ta? Yes. So the value, no, is 21.82 KSI. Then the nominal strength is from this critical buckling strength times the gross cross-sectional area equal to 2.7. So the answer for the nominal strength is 58.91 KSI. This is for the global, no? Global buckling. Then to compute for the local, no? This time is, we'll try to compute for the local buckling. So we have to check the width to thickness ratios, no? From AISC manual 13th edition, but we are using now 14th edition in table 1-11, page 1 to 80. Page 1-80, I mean. The width to thickness ratio for the larger overall dimension is, yes, we'll try to see this shape in the AISC manual to see the value for H over T and for the smaller dimension B over T. Of course, this H over T will govern, will prevail since this is the more critical, no, for local buckling. So atong tanawon sa AISC, no, manual. Unsa to? Table 1-11, no? This is table 1-11 for regular HSS. Yes. This H, okay, we have to, like, these values, kani siya, B over T and H over T. So, the HSS 8 by 4 by 1/8, the B over T is this value 31.5 for B over T, and for the longer dimension is 66.0, no? This one, the larger overall dimension will govern, no? Since this is critical, no? Than this smaller dimension. So this is we try to evaluate this one. Okay, yes, this is the table, no, that we tried to see, no, earlier. For B over T is 31.5 and H over T 66. Yes, from NACP table 502.4.1, the case 12, the upper limit for non-slender element is, yes, we discussed earlier, diba? This table 502.4.1, Stephen, the HSS, let me like go back to this one. B over 2. Case 12, non-slender element. Table 502 point. Okay, tanaw na to sa NACP. Table 502.4.1. This is 502. Itong table. This is 504, no? 502.4. 502.4.1. Yes, for case 12, Stephen, uniform compression in flanges of rectangular box and hollow structural sections of uniform thickness subject to bending or compression, flange, cover plates, and diaphragm. So this is, the problem is in case number 12, no? This is for the compact and the non-compact. So we'll try to evaluate this, non-compact, no, for the slender elements. Kung mo less than pa siya or mo greater than aning 1.40 square root of B over Fy. And compare with this with the B over T, no? Since we already get the B over T is actually the same with H over T, but the larger dimension will govern, no? Since this so this doesn't mean ang kaning B over T here is B over T sa katong sa AISC manual, but the larger value for the like the larger overall dimension divided by the thickness, so mo may mas dako, so mo siya ang mo govern, no? Try to compare this one with H over T, no? From NACP table 502.4 case 12, no, because this is uniform compression in flanges of rectangular box and hollow structural sections of uniform thickness subjected to bending or compression, no? So the upper limit for compact, no, non-compact, no, is this lambda sub r equal to 1.40 square root of B over Fy, which is equal to 35.15. And comparing the previous value H over T, which is 66, meaning greater than, diba? This width to thickness ratio exceed this 1.40 square root of B over Fy, meaning slender element siya, and the local buckling must be evaluated or computed. Note that B over T in the table is a generic notation, thus it applies to H over T as well. No? So, nabilong siya sa slender element. So, since the cross-sectional element is stiffened element, no, the Q sub S is 1.0, and the Q sub A must be computed from any CP 505.2 or 0.7.2 or AISC equation E7.2. The shape is a rectangular section of uniform thickness. Yes, since ang cross-sectional element, no, this element is stiffened, di ba? Meaning the Q sub S is equal to 1, and the Q sub A is, we have to compute. High shape. Projecting from built up columns or compression. Slender stiffened element. So, ang element is stiffened, and also, so, kailangan na to i-compute ang Q sub A. Ang Q sub S is, in this problem, since stiffened element man siya, Q sub S is already equal to 1 na siya. No? And also, in here, Q sub A, naa siya provision for flanges of square and rectangular shaped element sections of uniform thickness. Use B sub E, they reduce effective with this formula. So, maunang Q sub S is already equal to 1.0, and Q sub A, we have to compute Q sub A, no? And since B over T is greater than or equal to this 1.40 square root of E over F, which is the limiting value for non-compact, meaning after the non-compact, greater pa siya sa non-compact, slender na gid siya, yung local buckling. Kailangan nimo siya i-evaluate, no? And since like beyond naman siya sa non-compact, you have to compute the reduction factor Q, which is equal to Q sub S times Q sub A. No? Pero kung nasa within sa compact and non-compact, the Q sub S should be equal to 1 and Q sub A should be equal to 1. So that Q is equal to, just equal to 1. Pero kani beyond naman siya, no? Kani B over T, greater than naman siya sa non-compact, which is 1.40. Katong based on the table, this one is based on the table limiting value for the non-compact square root of E over F. Then use this F where F ini CP 505.7.2-2 or AISC E7.2, F is equal to Pn over the A effective. So this second condition, remember, yes, this is for flanges of square and rectangular slender element sections of uniform thickness, diba? HSS man tong problem, no, given. Use this reduce effective with where F, this small f, is equal to the nominal strength divided by the effective area, no? And Okay, to solve for the effective area, or reduce effective area, the specification user note for square and rectangular section permits a value of f is equal to fy to be used in lieu of determining f by iteration, no? From NSCP equation 505.7-18 or AISC equation E7-18. Effective width of the slender element is this equation, no? This is the second condition, no? Balik ta otro. Second, for flanges or of square and rectangular element, slender element sections of uniform thickness, HSS. Now, user note we have here, in lieu of calculating f, which requires iteration, f may be taken equal to fy, no? So, mo nang f is equal to fy. And fy is given, di ba? Fy is equal to, as given the problem, sige na tagbalik ka, 46 KSI. So, balik na punta. So, using this reduced effective width, so substitute this is the design thickness, no? Given in the figure. I mean, balik dito na lang ta sa dire. The design thickness 0.116, not the nominal thickness, ha? The design thickness should be used. So, manang 1 point, B sub E is equal to 1.92 times 0.116 square root of 29,000 over F should be taken as Fy, which is 46 KSI, times 1 minus 0.38. B over T, this is given the problem, no? Given in the table, no? Which equal to 66. This is equal to 66 square root of 29,000 KSI over 46, no? This is Fy. So that B sub E is equal to 4.784 inches. Then, from NSCP 502.4.2-4 or AISC B 4.1, close parenthesis B, close and open parenthesis B, and discussion in part 1 of the manual, the unreduced length of 8 inches side between the corner radii can be taken as B, or the actual width or height minus 3 times the design thickness. This is actually from NECP 502.4.2-4 atong tanawon sa NECP, no? From this provision, no? Nga ang B, to get the unreduced length, no? Unreduced length of the 8-inch side of those rectangular shape, atong tanawon sa to 502.4.2. This one. This is 502.4.2. Stiffened, yes, stiffened element. So, naa siya diri asa -4. Itong ipadako. This one. For flange of rectangular hollow structural sections, HSS, the width B is the clear distance between the web less the inside corner radius, di ba? Naaman tay ang HSS is naamgod siya like fillet sa isig kilid, di ba? Isig corner niya. So naa kay gitawag corner radius. So meaning kani siya is like quarter of a circle, di ba? Quarter of a circle. So naa kay like radius, no? Meaning corner radius also sa pikas and corner radius, di ba? Now, for flanges of rectangular hollow structural sections, HSS, the width B is the clear distance between web less the inside corner radius on each side. For webs of rectangular HSS, H is the clear distance between the flanges less the inside corner radius on each side. No? So this the B, the width and the height. The clear distance minus the corner radius each side. No? But if the corner radius is not known, no, kani siya, is not known, B and H shall be taken as the corresponding outside dimensions minus 3 times the thickness. The thickness T shall be taken as the design wall thickness. Not the nominal thickness, but the design thickness. So, mo nang, from this INICP 502.4.2-4, actually this is 3. No? 502.4.3. This should be 3. Ang hinayan ang thickness. Hinayan. Gamyan ang. This should be 3, no? From the NACP. Or AISCB 4.1b. The discussion in part 1 of the manual. The unreduced length of 8-inch side between the corner radii can be taken as B is equal to 8, diba? 8, which is this 8, the height, the total height, minus 3 times the design thickness. Design thickness is 0.116, diba? Yes. From the NSCP, the corresponding outside dimension minus 3 times the thickness. The thickness T shall be taken as the design wall thickness. Diba? So, maunang 8, the height, total height of the HSS shape minus 3 times the design thickness. So, this is the unreduced length, no? Reduced length of the 8-inch side equal to 7.652 inches, where the corner radius is taken as 1.5 times the design thickness. Okay, since unknown man ang atong corner radius, but actually the corner radius taken as 1.5 times the design thickness. So we still use this the height, total height minus 3 times the design thickness. Therefore, the total loss in area is okay, we have to compute the total loss area in the height lang siya. Height lang siya, no? So, manang 2 for the 2 height. Diba kay HSS man to. So, B, which is this actually the unreduced length. So, nang 2 times B minus the effective reduced B. B sub E is this is the loss, no? This is the loss area, total loss area. So, maunang total loss in the area. So, 2 times the B, the unreduced length, no? 7.652 minus the effective width, which is computed earlier, 4.784 times the design thickness, no? This is not the nominal thickness, this is still the design thickness, no? In the computation, T is the design thickness. The total loss area, no? I think this is how to say in English. I think this is understandable, no? Sabotable. So the answer is the total area, therefore, total loss in area is 0.6654. Kani siya, since this total loss area, mo ni siyang i-minus sa gross area. Therefore, the reduced area or the A effective is the gross area minus this total loss in the area. Diba? Because this is the unreduced length and minus the effective. So, bali ang na-loss aning width times the thickness. Then, times 2 since duha man to ang height sa HSS shape. So, manang effective, A effective is equal to 2 point gross area minus this loss, total loss in the area. So, that the reduction factor Q sub A is given as effective area over the gross area, diba? Which is equal to 0.7. Therefore, Q sub A is 0.7537. And since Q is equal to Q sub S times Q sub A for slender element, no, or for those element nga beyond na sa non-compact. So 1.0 times 0.537. So that Q is 0.7537. So taas kay siya nga solution. But this problem is also in the book of Sigui 2013, no? Then, since we already computed this Q, substitute this Q for this equation, di ba? Since we have the reduction factor Q, this equation is actually 4.47 square root of E over Fy Q, no? Times Q. Balik tayo dito sa Q. Yes, this one. Diba? So, you have to compare the KL over R using the reduction factor Q. No? Square root of E over Q of Y. So, atong tanawon, we already computed Q, no? Reduction factor. So, this 4.71 square root of E over Q Fy, the answer is 136.2. Diba? But the KL over R, which we already computed, the slenderness ratio in the beginning of this solution is 105.3, which is greater than, less than, which is less than this value. So, if this is less than, no, balik ta, thus use NECP equation 505.7-2 or AISCE 7. Balik ta sa kuan. Less than ang KL over R, di ba? If KL over R is less than, nato sa, yes, this one, no? Use equation 505.2-2 or AIS equation E7-2. If KL over R is less than this value, use FCR equal to Q times 0.658. Q Fy over Fe times Fy. So, balik ta again na pod sa, okay, dire, no? So, KL over R is less than. So, use this critical buckling load equal to Q times 0.658 Q Fy Fe. No? Substitute lang ka those values. The answer is 19.76 KSI. Then, this is the critical buckling strength. Critical buckling strength. Then, to compute for the nominal strength, times ka og, this is in stress, no? In kilopounds per square inch. Then, to convert for the nominal load or nominal strength is times the gross area, no? FCR times the gross area. So that the nominal load, no, is 53.35 kilopounds. As notice, no, since this is less than the flexural buckling strength or the global buckling strength of 58.91 kilopounds, meaning the local buckling controls, no? The nominal strength yun ni siya, di ba? Meaning this is the strength nga or load nga ma-carry sa, it should not exceed. Since less than man siya than the flexural, meaning kini nga buckling, this is for the buckling, local buckling, meaning this will control, no, in the design. Flexural buckling strength is katong na compute to ganina, global, is equal to, ano naman to, this one, global buckling 58.21. So the local buckling controls, no, and to get the design strength or the allowable strength, a design strength for LRFD, you have to multiply with the resistance factor phi sub c or 0.9, no, since this will control so manang 53.35 kilopounds. So the answer, design strength, meaning dapat dili siya mo lapas ani 58 kilopounds for LRFD, and for ASD is divide by this factor of safety 1.67. The answer is 32 kilopounds, or in terms of stress is 0 times the critical buckling strength or the local buckling strength, or just divide this one by the, in these kilopounds, divide by the area 2 gross area 2.7. So mo ra gyapon ang actually ang answer. $11.932 11.852, no? Ato lang i-erase para di mo mag nalibog. So we're done with determining the design strength now for LRFD and ASD. By first is you have to get the flexural buckling strength or the global buckling strength. Then also you have to check for the local buckling, no, using those provisions or conditions that was discussed. And next is alternative solution with F, determined by iteration. Okay, let's discuss this one.